Welcome to our presentation on operating system structures. In this session, we will explore the various components and services provided by operating systems. Operating systems provide an environment for executing programs and services. They offer functions that are essential for user interaction, such as command line interfaces, graphical user interfaces, and batch processing. The system must be capable of loading programs into memory, executing them, and handling their termination. Additionally, running programs may require input and output operations involving files or devices. Operating systems manage file systems, allowing programs to read, write, and manipulate files and directories. They also facilitate communication between processes, whether on the same computer or over a network. Operating systems must constantly monitor for errors in the CPU, memory, I/O devices, and user programs. They take appropriate actions to ensure correct and consistent computing, enhancing user and programmer efficiency. To ensure efficient system operation, operating systems allocate resources like CPU cycles, memory, and storage to multiple users and jobs. They also track resource usage to manage system performance. Operating systems enforce protection and security measures to control access to system resources and defend against unauthorized access. This ensures that concurrent processes do not interfere with each other. This diagram provides a visual representation of the various services offered by operating systems, including user interfaces, system calls, and essential services like error detection and resource allocation. The command line interface is a text-based interface that allows users to interact with the operating system by typing commands. It can be implemented in the kernel or as a system program. Here, we see an example of the MS-DOS command interpreter, which allows users to execute commands directly in a text-based environment. This slide shows a shell command interpreter, which is another example of a text-based interface for interacting with the operating system. Graphical user interfaces include elements like windows, icons, and buttons, allowing users to interact with the system visually. Many systems support both CLI and GUI interfaces. Touchscreen devices require new interfaces that rely on gestures and virtual keyboards for interaction, as traditional mouse and keyboard inputs are not feasible. System calls are the mechanisms through which programs interact with the operating system. They provide essential services to user programs via application program interfaces. This diagram illustrates the relationship between user applications, system calls, and the operating system, highlighting how system calls facilitate communication between user mode and kernel mode. Each system call is associated with a unique number. The system call interface maintains a table indexed by these numbers, invoking the appropriate system call in the OS kernel. Parameters for system calls can be passed in various ways, including through registers, memory blocks, or the stack. This ensures that the operating system receives the necessary information to execute the call. This diagram shows how parameters for system calls can be passed via a table, with the operating system retrieving the necessary information from the table to execute the call. System calls can be categorized into types such as process control, which includes creating and terminating processes, and file management, which involves operations like opening, closing, and reading files. Other types of system calls include device management, which handles device requests and attributes, and information maintenance, which manages system data and attributes. System calls are essential for managing various operations in an operating system. They can be categorized into protection, which controls access to resources and user permissions, and communications, which handle the creation and deletion of communication connections, message passing, and shared memory models. Here, we see a comparison of system calls between Windows and Unix. Each operating system has its own set of calls for process control, file manipulation, device management, information maintenance, communication, and protection. System programs are crucial for programming the operating system software. They provide a convenient environment for development and execution, and can be divided into categories such as file management, status information, programming language support, program loading and execution, communications, background services, and application programs. File management involves creating, deleting, copying, and manipulating files and directories. Status information provides system data like date, time, and disk space. File modification includes using text editors and special commands to search and transform text. Programming language support includes compilers and debuggers. Program loading and execution involve loaders and debugging systems. Communications provide mechanisms for virtual connections and allow users to send messages and transfer files. Background services launch at boot time and handle tasks like disk checking and error logging. Application programs are run by users and are not typically considered part of the OS, being launched via command line or mouse click. The design and implementation of an operating system start with defining goals and specifications. User goals focus on convenience, ease of use, and safety, while system goals emphasize ease of design, implementation, and maintenance. Separating policy from mechanism is crucial for flexibility. Policies decide what will be done, while mechanisms determine how to do it. This separation is a key principle in software engineering for OS design. Operating systems have evolved from assembly language to high-level languages like C and C++. Modern OS implementations use a mix of languages, balancing low-level efficiency with high-level portability and functionality. The structure of an operating system can vary, with different approaches like simple structure, layered approach, microkernel, modular, and hybrid systems. Each has its own method of organizing OS components. MS-DOS started as a simple system with limited functionality, designed to provide the most functionality in the least space. It has some structure but lacks clear separation between interfaces and functionality levels. Unix uses a layered approach, with each layer built on top of the lower ones. The bottom layer is the hardware, and the highest layer is the user interface. This structure simplifies construction and debugging. Unix OS is divided into systems programs and the kernel. This separation allows for better organization and management of hardware functionality and system operations. Mac structures the OS by removing non-essential components from the kernel and implementing them as user-level programs. Communication between user modules occurs through message passing. Linux uses a modular approach with loadable kernel modules. Each core component is separate and communicates over known interfaces, providing flexibility similar to layers but with more adaptability. iOS, developed by Apple, is a mobile operating system for iPhone and iPad. It includes layers like Cocoa Touch for app development, media services for graphics and audio, core services for cloud computing, and Core OS based on the Mac OS X kernel. Android, developed by the Open Handset Alliance led by Google, is based on a modified Linux kernel. It is designed for touchscreen devices and includes process, memory, and power management features. Debugging involves finding and fixing errors. OSes generate log files with error information, and failures can create core dump or crash dump files to capture memory states for analysis. Performance tuning improves system performance by removing bottlenecks. OSes provide tools to measure and display system behavior, such as the Windows Task Manager. System generation, or sysgen, creates a unique instance of an OS by combining user-specified options with general-purpose code. This process builds a system-specific compiled kernel for efficient operation. Booting is the startup sequence that initializes the OS. It starts at a fixed memory location, with the firmware ROM holding the initial boot code. The bootstrap loader then loads the kernel into memory and starts it.